This is Bartolome Tomic with Marine Technology TV, and we're here today with Dr. Martin Furlong, head of the Marine Autonomous and Robotic Systems Group at the National Oceanography Center in the UK, to discuss the evolution of the AUVs. Dr. Furlong, can you please provide a brief overview of your career with insights on the scope of your current position and responsibilities?
Okay, so I'm Dr. Martin Furlong. I head up currently the Marine Autonomous and Robotic Systems Group at NOC. I started at NOC in 2000. I was doing what was called an engineering doctorate, and this is a bit like a PhD and a master's and some on-site training all bolted together. It was supposed to sort of create leaders of industry, I think was the pitch at the time. So I started at NOC. I was working with the Autonomous Underwater Vehicle Group, and I was looking at sort of hydrodynamics and system identification of hydrodynamic derivatives of AUVs. So basically just how you can model them as they move through the water. Specific area of interest was when they go slowly and how their sort of like their flight characteristics deteriorate for the sort of vehicles which we work on at NOC. After I finished my doctorate, I joined NOC as part of the Autonomous Underwater Vehicle Group, and I worked with that sort of team, we call it the AutoSub team, until 2012, 2013, I think it was 2013. I then took over as head of the Marine Autonomous and Robotic Systems Group. And so what MARS covers is it covers the AUV group, so the bigger AUVs. We also have a glider team, and we call it a long range team, so it does gliders, long range unmanned surface vessels, and also homegrown long range AUVs. And we also have an ROV team. And so this runs one of Europe's, I guess, premier 6,500 meter rated science ROVs. And alongside the operational side, we also have a development team, which I sort of oversee, which is actually led by Dr. Alex Phillips. And so we have a strong operational component, but also a really, really strong development component.
So as NOC recently celebrated the 25th anniversary of its first autonomous underwater vehicle, or its mission, can you put in perspective the importance of unmanned autonomous systems to accomplishing the overall mission of the National Oceanography Center?
As an engineer, I love AUVs, and and all marine autonomous systems and robotics is just is great. But the Oceanography Center is actually here to deliver science. So these vehicles are basically just taxis for sensors. And they're part of the toolkit that we have to undertake in situ measurements within the world's oceans. So they're important and they're growing in importance, certainly as we move towards sort of net zero sort of oceanographic capabilities and the drive to actually reduce the carbon impact of oceanographic science. But they're not everything, but they do have some unique capabilities. So a lot of the early work we were doing with AUVs was around under ice deployments. And so it's very, very difficult to get your sensors under ice with a ship. So you can't batter through the ice, so you need to go and send something underneath to go and do the measurements. They also work incredibly well when you're in the deep ocean and you want to do high resolution multi-beam maps, because you can't really effectively do that from a ship. I mean, there's some capability to use towed instruments, but it just doesn't work as well in like 6,000 meters of water. Obviously the ROVs, we all know ROVs, they're really, really useful for sort of a specific subset of measurement capabilities, but we also have a really strong glider component. And these subsea gliders, they allow you to do sort of oceanographic measurements to understand the water properties. So it's like primarily temperature and salinity, but they're also looking at some of the biogeochemical type measurements as well. And these vehicles have an incredibly long range. So they're sort of, 5,000-6,000 kilometers a year being deployed, where they can go around and effectively take measurements when you couldn't send a ship out for that sort of amount of time. So they form part of the toolbox to allow us to actually study the oceans, but they are growing in importance as they get more capable. And as I said, the drive towards sort of reducing the carbon impact of things.
Thank you. While I know there have been many in looking over the last 2.5 decades of AUV development at NOC, sorry, what do you count as the pinnacle events, the top 3 or 4 or 5 developments or highlights?
It's really, really difficult. I mean, it's one of the, I mean, when I was
Name
looking,
1, 2.
well, I can name a few. So I was just
Right.
going to sit there and say, from a operational point of view, so some of the really groundbreaking, exciting things we've done, some of the really early under ice work. So this was sort of 2000 through to about 2004. We also have with AutoSub 3, we did a whole load of really groundbreaking work. It was in 2009, going underneath the sort of ice shelf in Antarctica. And that we got in sort of like 60 kilometers in from the actual front of the ice. So imagine you get the big glass that goes out to sea, you get the front and you go in 60 kilometers and you do a load of measurements and you turn around and come back. So that was AutoSub 3, AutoSub 6000. We found the deepest yet discovered hydrothermal vent in the Mid-Cayman Rise using the vehicle, as well as a number of other vent fields. So that was really successful. We've also, with AutoSub 6000, we've done mapping of the Whittard Canyon. And so effectively, you look at the UK, you go sort of the southwest and there's the shelf break. So it's where it drops from like 200 meters to like 4,000 meters. And there's these canyon structures. And we were using AutoSub 6000 along with ISIS to, which is the deep ROV, and the ship, which is the James Cook, to actually measure or multi-beam the side of the canyon. And so traditionally with an AUV, you just look downwards. In this case, we changed the AUV to the side. We were navigating this really complex terrain and actually getting really good imagery of the effectively the sides of Whittard Canyon. If we then move to a different flavor of vehicles, so these are the AutoSub long range vehicles, which are again homegrown, internally designed platforms. That went out and did the a glacier or deployment under another Antarctic glacier in sort of, I think it was 2017, 2018. And again, it sort of like went in sort of like, 40, 50 kilometers under the ice, doing a whole load of surveys. And we had 2 deployments under the ice for that. So those are sort of some of the highlights, but every campaign has its successes and challenges. And so pretty much, the vast majority of them have led to really interesting science and really moved, our understanding of the world's oceans forward.
Thank you. So can you give our viewers an update and overview, a by the numbers look using the metrics of your choice of the autonomous fleet deployed by the NOC today?
So we have a very large high-powered AUV, so it's a 6,000 meter rated AUV, which we've just retired, which is called AutoSub 6000, and we're replacing that with the naming convention is a bit odd, but we're calling it AutoSub 5, and so it's effectively our 5th generation high-powered AUV. So we have one of those. We have 6 AutoSub long-range vehicles, and so we have 3 that are 6,000 meter rated, and we have 3 that are 1,500 meter rated. The difference between the 2 is that as you can trade depth rating for the amount of batteries that you can put on board. The 1,500 variant is about 6,000 kilometers, sort of 3 or 4 month endurance, whereas the 6,000 meter variant is sort of, it's about 2,000 kilometers, maybe sort of, a month to 6 weeks endurance. We also have a 6,500 meter rated ROV. We have a remotely operated vehicle, which is another 6,000 meter rated system. This is a bit like an ROV, but it doesn't have any syntactic foam. It integrates onto our research vessels, which is the RRS James Cook and the RRS Discovery. And we also run a fleet of approximately 40 gliders. We have a whole different set of varieties. So we have a mix of Teledyne Web Slocums, and we probably maybe 25 of those. We have, I think it's about 12 or 13 sea gliders. Again, these are 1,000 meter rated systems. And then we have, I think, Europe's only deep glider. So this is a variant of the sea gliders, and this is It's a 4,000 meter rated glider. And then within the Teledyne web gliders, we have a number of G2s, which is the sort of previous generation G3s, and some of them run microstructure turbulence probes, some of them have extended energy bays, some of them have ADCPs, and so on and so forth. So there's, you know, we've got quite a lot of stuff.
There's a lot. Yeah. You mentioned naming conventions. Am I wrong I read somewhere that there is a AUV called Bodie McBoatface?
Yes. So we call Bodie McBoatface auto sublong range. But because of the timing of the developments of auto sublong range, or the ALR 1500 variant, it was decided by the National Environment Research Council to not name the Sir David Attenborough Bodie McBoatface, but name the AUVs Bodie McBoatface. So Bodie McBoatface is the auto sublong range vehicles, and I mean they're great systems, and they're they sit in a very unusual category for these type of platforms. It tends to be you either have ocean-going gliders, which are very small, very low powered and very slow, or you have very big, high-powered, short-range vehicles. And the auto sublong range platforms sit in the middle. So they are very long range. They're not as fast as the bigger platforms, but they're still quite a lot faster than the gliders, and they can carry a far larger sensor payload.
Yeah, thank you. Looking to the future, what is NOC working on now? What are the key technologies, enablers, and drivers that will help make autonomous vessels even more integral to your operations?
So on a technology front, we are building, I mean, weirdly, everything's a software problem now. So we're building the control systems which sit in the vehicle. We're using something called the robot operating system as our primary platform, and we're building the software architecture on that. But the key thing for us is to build effectively, it's a front seat. We run a front seat, back seat paradigm. And the easiest way of thinking about this is that the front seat is the bit that we control, and it's like the taxi driver, whereas you can have passengers in the back which tell the taxi driver where they want to go, and the taxi driver makes sure it's safe, but it cedes a reasonable amount of control to the back seat. And the reason we do this is it enables other people to generate algorithms which can increase the capabilities of the vehicle. And so you might have algorithms for following fronts, or for sort of adaptive mission planning, and you can allow other people to build those algorithms and then link them into your system so that you can actually increase the capabilities of it. So at a vehicle level, that's what we're building. But we're also building a sort of a shoreside infrastructure, and we call this it's a sort of command and control and data ecosystem. And so what you need to think about is that these in situ measurements that are generated by these vehicles, they need to be fed back to NOC and then distributed effectively into what's called the global ocean observing system. So people want to understand how the global oceans are working. They want to share all their data. And so what we're trying to do is build those data pathways from the vehicles back to NOC, and then distribute them out into the global ocean observing system. So that's one element of the command and control and data ecosystem, and that's the data ecosystem side. On the command and control side, we also want to have big fleets of vehicles that we can sort of autonomously task. And so at the moment we're trying to build them so that you have a nice interface, so you can drive these vehicles around, and you can have a heterogeneous fleet and you can understand what they're all doing. But we also then want to be able to build computer algorithms which will tell the vehicles where to go based on, I don't know, satellite information, model information, and all the rest of it. So that command and control system, it needs a similar sort of front seat, back seat paradigm. So it will sit there and have a layer which means that the commands sent to the vehicles mean it's safe, but you want to build sort of like a back seat sort of algorithms that third parties can generate for actually moving these vehicles around. So a scientist might sit there and go, I've got this great model, that model is going to drive where I want to send these vehicles. And so we would just expose them the relevant APIs, which they can then send to us, which then means we will pass it, make sure it's safe, and then send it to the vehicles. Because you don't want them to sit there and have a problem with their algorithm, which says, you know, drive my vehicle to the middle of, I don't know, Chelsea or something, and you just go, well, it's going to collide with the shore and it's going to get destroyed. So a lot of the work we're doing, although we're building platforms and we're very strong at platforms development, a lot of this is around building the software architectures, both for the vehicle and for the sort of top side, shore side control and data ecosystem. And the final element which we're working on is trying to, with the vehicles, make them incredibly modular. And so we want to sort of standard battery packs, standard thrusters, standard navigation packs, you know, standard everything, because then you can repackage them. And so you might sit there and go, I want a 6,000 meter rated vehicle to go and do this. And then we might say, well, we want a crawler, which is, you know, you think it's entirely different, but it's still got battery packs, power tubes, logging tubes, you know, and similar like motors and thrusters. And so by using very modular technology, you can then just repackage it, and suddenly you've got a new vehicle which looks significantly different than, you know, your typical AUV, but actually shares a lot of common components. And so it just allows us to do it more rapidly and more reliably.
And cheaper, probably, right?
Yeah. I mean, all the cost is development, really. I mean, buying the equipment is expensive, but most of it sits in labor, just for actually designing and developing things. So if you've got, you know, if you designed it once and you can share it over lots of vehicles, it makes a significant difference.
Thanks. Also, to end this interesting interview, can you discuss one or two recent, current, or future expeditions that highlight the value of the NOC Autonomous Fleet? But before you do that, I was Googling the way to pronounce your name. So I got it right, Martin, right?
Yeah.
And I saw your name linked to some kind of celebration at the Loch Ness. So does it mean that you were searching for Nessie?
So we've spent a long time trying to find good trial sites for AUVs in the UK, and it's, you know, you effectively need a big body of water which is suitably deep and, you know, preferably quite quiet, with good shoreside access. And it turns out that Loch Ness is like probably the premier place to test AUVs within the UK. And so for us, it's like we will load everything into a lorry, send it up to Loch Ness to deploy vehicles. So we have not yet found Nessie. We believe there's a lot of other stuff down there for us to go and find. One of which is that we actually lost an instrument there a few years ago, where we had a vehicle, we deployed it, and it was talking to us, and then it wasn't talking to us, and it hasn't talked to us for about 2 years. So we think on the bottom of Loch Ness there may well be a subsea glider with our name on it.
So, but now seriously, is there a current or future expedition that you would like to talk about or share something interesting?
So we actually have a number. I mean, the most imminent one is that we are sending one of the auto sub-long range vehicles down to Thwaites Glacier as part of there's a Tarzan project, which is part of the International Thwaites Glacier campaign. And so this is going out on, the team are actually flying out, I think, on Saturday to go down there. And it's a long old expedition because of COVID restrictions. But they are effectively going to be away for 100 days, but they are going to go down on the Nathaniel B. Palmer, get to the Thwaites Glacier and deploy the ALR under ice as part of a big measurement campaign down there. So that's really exciting. We're really looking forward to that. We've done a lot of trials beforehand to de-risk it. And so, you know, we're hoping for, you know, lots of success with that. So we have that coming up. Next year, we have another ALR, which is being deployed from Shetland, which is going to go and visit a number of decommissioned oil and gas infrastructure. I think it's looking at about 750 kilometers sort of round trip, where we'll go and look at these different sites with like cameras and other sort of chemical sensors. We also have a long distance proving trial for the ALR, which I think is looking like 2,500 kilometers, probably going out from Plymouth to the Shelf Break. So we're doing that. And then we're also have a really exciting set of campaigns and missions with the AutoSub 5 vehicle, which is our new deep diving AUV, which is going to go back to Whittard Canyon, which is going to go and do a whole load of survey work with the ROV, as well as actually just sort of generating data itself. So it's going to be another busy year. I mean, we've been we're not slowing down. There's a huge amount happening, and there's huge amounts of developments happening, and that's just a small fraction of what's sort of going on at NOC. The other thing that we're focused on at the moment as well is this transition towards sort of net zero. So there is a goal for the oceanographic fleet and the capabilities to be net zero by 2040. So there's a huge amount of work to be done, both on the ships, but also using longer range marine autonomous systems to actually transition towards net zero. And so there will be a lot of development work and a lot of trials and a lot of integration of new sensors to enable the long range fleets to be able to hit that net zero goal by 2040. So yeah, it's all exciting stuff, and it's and we're certainly busy with lots of interesting things happening.